Okay.
No.
I know. Just making sure. Feels weird. Whatever. Okay. Good enough. There we go. Dish. Okay, it's been a little finicky, but it was working well when we were working on it earlier. But regardless, we are the CO2 Bros. We are Team 8, and we are here with our final presentation. So to kick it off, I am Michael Ferrone. I am the team captain. I did the 3D modelings of parts, and I helped out with some of the coding.
I'm Jin, and I was doing the circuit design, and I was working with the power of the board as well.
My name is Joe Heiser, and I did a lot of the circuit design and the embedded software.
And I'm Ryan Alesna, and I did the software development for this project.
So in our final presentation here, we have a couple things we're going to be going over today. And so the first thing we're starting with is the problem statement, needs and requirements. Then we're going to be talking about the solution demonstration, but we're getting a little bit of a sneak peek of that now. We're doing the software integration and test results, electronics integration and test results, physical enclosure integration and test results, and then finishing off with project management and learnings. So our problem statement is, due to the increase in public face mask usage, the ability to communicate clearly indoors has become an issue. This is obviously unique with the COVID pandemic, and even though most people have stopped wearing masks for their own reasons, the prevalence is still much higher than it was, and so we have noticed that it's a lot harder to talk indoors or to communicate clearly indoors. And so our solution needs to be affordable, be lightweight and portable, not compromise the mask protection, and needs to be reusable. So we have a lot of requirements here. We're going to be covering each of them specifically and how we went through and proved them all. We do have one, it's a little bit cut off on this screen, but it's the maximum volume. We did have a speaker initially in our setup that would amplify the user's voice, but because of different limitations on our semester, we had to end up removing that. And so we have left out that requirement, but we have all of our constraints, which are still completely met. And yeah, they are all met. We don't go into much depth in them, but they are met completely. And now moving on to the solution demonstration, we have Jen.
So as you can see, when he was talking, he showed a demo preview of what our solution looks like. So I'm gonna go over how you can take off the mask nice and easy. So you first remove one side of the from the backing, and then simply just take it off. Make sure you hold on to the back piece. And to put it on, you need to make sure that the mask is slipped between the backing here, and then the sensor is inside the mask while the screen is outside. And so that thing's on nice and tight. So Michael is then put on the mask like how he usually does with the mask before he clip it onto the backing. So once the mask is on, you put the backing on the back of your head, and then chooses whatever so that's such as adjustable. There's like 3 different levels of it if you want to turn around. So there's 3 different levels of it. You can choose based on your size, so that's such that it's tight on your face. And if Michael, you want to turn it on and show another demo of it.
It's a little bit hard for the user to know if it's working on it properly, but
So yeah, the sensor in there needs to be set tight on your bottom lip such that it works pretty well
yes.
in our communication. So our first requirement is that there's a clear communication over a certain distance. For us, we identified that range to be 4 to 25 feet. And this picture right here was taken at 25 feet, but it's a zoomed in view. So if we take a Michael, if you want to, I guess it's about 25 feet in here, but
it's pretty far.
Yeah, you could see the lip moving and stuff at 25 feet apart. And we gone through the solution demo, and I'll hand over to Ryan. He was going to talk to you about how the software works and the test results we have for that.
Thanks, Jen. So initially, when we were coming into this project, I guess 2 semesters ago, this was our initial flow diagram that we were looking at. So we had sort of 2 different sections. We had our input audio stream through a microphone, and then we had mouth movement through a motion sensor. We are going to link these up and basically make sure that if both are happening, then we're going to actually go forward with our movement process. Now, With our actual project, we learned that there were a lot of software and hardware limitations to this. And because of that, we kind of had to adjust it a little bit. So we couldn't get real-time speech to text actually working. Because of the ESP32, it doesn't have enough processing power to actually do real-time in C. Initially, we had it in Python, but then there was a hardware compatibility issue where we couldn't use specific drivers in Python, libraries in Python. So it kind of got pretty messy pretty quickly. So because of that right now, our speech to text is not really implemented too much. Instead, we're just working directly with the motion sensor because of that hardware limitation. So as we can see here, we're waiting for input state. It's just going to basically continuously look for any sort of movement. We have our mouth movement and our motion sensor. The way that we're kind of doing that and determining what's actually happening is we're taking the average slope and distance between the motion sensor and the mouth over 20 millisecond intervals. And if the slope is negative, it means that the mouth is closing. If the slope is positive, it means the mouth is opening. And here, this is where our next requirement is going to come out of here, this displaying mouse shape based on the input that comes in. So our second requirement is % of human speech detected. And we wanted to make sure that, it's actually going to be somewhat accurate and it's not just going to be doing random things. So it's actually useful. So what we did was we had 2 input messages, and in order to compare, we counted the syllables in the input message. And a pretty general idea is that when you open and close your mouth, that counts as 1 syllable or 1 word if it's a 1 syllable word. So what we did was we counted the syllables in the input message, we put the mask on, and we had the person wearing the mask say the sentence. We counted how many times it opened and closed. And so for this top one, we had 12 out of 16 syllables displayed, which is a pass because our pass criteria was 70 to 100%. Obviously, we want it to be 100, but a lot of the times that's not exactly reasonable. So this was a 75% pass rate. And then for our second one, we had 12 out of 14, which is around a 79% pass rate. We had a lot of software challenges when doing this project, but I kind of talked about it a little bit. But first one was the software and the hardware compatibility. With the ESP32, it allows us to use MicroPython, but in MicroPython, it's missing key libraries for audio. So it kind of messes things up because we couldn't use our initial speech to text algorithm, which was indeed working in real time. And then with C, the ESP32 doesn't have enough processing power to actually do it in real time. So we could do it delayed, but it wasn't in real time. And then finally, a weird, well-known bug with the ESP32 is that you can't connect it to Wi-Fi networks that have spaces in the name. So for example, if we were trying to connect to a hotspot and it was Ryan's iPhone and it had space in between, it wouldn't be able to connect. So he had to completely change the name of the network in order for it to actually connect to the Wi-Fi. That's all for software, and I'm going to pass it to Joe for electronics.
Cool. Thanks, Ryan. So I'm going to talk about the electronics integration and our test results. So first up, here's our final PCBs. So on the left, we have the second version of our what we call mainboard PCB, which is 50 by 38 millimeters. So it fits in that the square case that was on Michael's face earlier. And on the right here is our sensor board and microphone PCB. And that is 22 by 7 millimeters. And that actually fits on the inside of the mask in a little housing there. Yeah, next slide. So for system functionality, I didn't really go too much into the actual circuitry of the previous 2 PCBs, but here's a quick overview of the whole system. So as you can see, like I mentioned, the PCB is mounted in this 3D printed plastic case. And it has our 2 flexible OLED screens connected to these 2 connectors here through flat flex cables. And they're supported by a wire. And then the sensor board up in this smaller case is also mounted on a wire and it has the mic and sensor, and it connects with 5 wires down to the main board PCB. And on the bottom here, we have our 2 battery wires kind of running off the screen, and that's how it's powered. Next slide. So some of our requirements for the electronics section are duration of hands-free operation. So optimally, we'd like to have 5 hours of hands-free operation. An acceptable range is 3 to 5 hours. And we tested the battery duration at 3.5 hours, fully charged. And that's running the screen at 100% brightness. So kind of the worst case scenario, we can get 3.5 hours. And it would be reasonable to get like a battery with twice the size, with twice the capacity. That's almost the same physical size, which should in turn double the battery life. And then another requirement is the amount of recharges. So this is hard to test with batteries without specialized test equipment for testing this. So like the cycle life of the battery, but based off of, first I'll start, the ideal amount of recharges cycles is 500, an acceptable range is around 800 to 500. Based on the data sheet from the battery, we have after 180 cycles, the battery retains 80% of its original capacity. So you still have like 3-ish hours, a little bit less of runtime after 180 cycles, and the battery will continue to degrade over time, but it's still usable for quite a while, quite more than 180 cycles. Next slide. So some of our challenges for the electronics. I'll start with some things that were sort of easy to fix, and then go on to one of the major issues that we had to redesign the board for. So starting with the RX and TX, so that's the receive and transmit between our ESP32 and our UART chip. And the UART chip is what allows us to connect to the computer and program the ESP32. So on the original iteration of the board, these were connected backwards. So essentially RX to RX and TX to TX, which does not work. You can't receive to another receive port. You have the RX to TX and then TX to RX. Thankfully, we were able to fix this on our first board by cutting some traces and soldering some small wires on. That allowed us to then start programming our custom board and uploading custom software. Secondly, the auto boot mode issue on the ESP32. So the ESP32 needs to be in bootloader mode to upload software to it. And originally, there was no functionality on our custom board to do this automatically, so over USB. So we had to use a jumper wire to short one of the pins on the ESP32 manually to put it into bootloader mode each time. And this was hard. It was kind of a 2-person operation. Like somebody had to hold the wires, somebody had to click the switch. It took a lot of time. And that definitely slowed down our software development and iteration. So we fixed that on the second version of the board. And the third issue here is I'm going to talk about is why we really had to make that second version. So the screen connectors that we got from Mouser, the footprint or the pinout, so like the connections of the actual screen to our board, from the footprint we downloaded from Mouser were actually incorrect. And the ones on Mouser are designed by community members, so it's not really like a verified source of footprints. And yeah, it was wrong on the first iteration. So, and that's not something that could be fixed by moving around jumper wires or things, like cutting traces on our board. It was too small of the spacing for the pins, so we had to redesign our board, make a second version. And since we were redesigning the board anyways, we then added the auto bootloader mode, and we fixed the RX and TX on the actual PCB. So our current version of the board has no after the fact modifications. It's all good to go. Yeah, and that's it for the electronics integration test results. Now we're going to go to Michael for some physical enclosure information.
So with the physical enclosure, there were 2 main housing boards. There was a third one created for the speaker, but since we're not using that, it's not present here, but it looks great, I promise. The main board here is obviously this big board that had to encapsulate all of the big circuit board and then make sure we had space for everything to get in and out and also serve as the main structural component for everything. And then the smaller board just needed holes for the speaker and the mic, or the sensor and the mic to get out, and then obviously wires for that. And so these led into 2 different requirements. The first requirement is obviously weight. Because this is going to be on your face, it can't be weighing down that much. This battery we're able to offset it would usually take on most of the weight just by itself, but with it having it on the back of the head, it wasn't too much of a drag on the actual mask itself. So we had within 15 to 35 grams, and it was within that with 32.3 grams, and with redesign and actually flushing out the design, because right now there's a lot of hot glue on here, so that weighs it down. But with better design, with more intent to like knowing exactly how he wants to do this, we can get it even lower. But as it stands, I've been the one majorly testing it, And it's not noticeable, especially with the back strap actually relieving the stress off of your ears. And so the next requirement, we have dust and moisture protection. So we wanted a relative IP51 when we figured that would give us the best protection against what we actually set out for. And with the lab we were working in, it was quite dusty already. So at the behest of Dr. Z, we said we already have our dust protection. And then from our extensive testing with the board, there's no external protection here or here, but obviously with it so close to somebody's mouth, it's going to get like water up in it, and it's still completely functional and no loss of functionality at all. And so with the housing challenges, we did have a little bit of a challenge right here, especially with this main board here. We had that's the power switch. It's very small. And so to actually reach in there, it was difficult. So we have a 3D printed component, which actually raises the switch, which makes it a lot easier to do. And so instead of having to be like, hey, can you please click it? You can actually do it yourself, which is very important for this. And then another part was the cable management. Obviously, with all these wires running around on your face, it can feel very weird just to have it rubbing up against your face, or I mean, just trying to manage it all right there. And then especially for the screen, these cables are very fragile, so you need to make sure it's actually sturdy. And so with some obviously helper wires, and this is what goes into the stability of it, we're able to hold these in place and actually try to manage things in best a way to where it's not as noticeable and you're not at fear of, oh, if I open my mouth too big, something's going to come unplugged. Everything is firmly in there, and the screen and sensor board are in positions where they're not moving around too much, so you don't have to worry about, oh, if I take too big a yawn, is it still going to keep sensing? It's held in a place where it's actually going to keep continuous sensing it. And so now I'm going to pass it to Jim to talk about project management and the rest of our accomplishments and challenges.
All right, thanks, Michael. So for our final requirement, we have the cost. For our cost, we wanted between $50 to $80. But as we can see over here, this is for 1 unit production, while the other one's for 10,000 unit production. In both cases, we see that the screen that we're using takes up majority of the cost for it. Then one way to get around that, we should maybe find another type of screen that's also flexible, and to drive down the cost so that we can actually get to our ideal cost or even below it. And so here is the overall requirement table that we have, and it shows that we have met all the requirement tables that's within the acceptable range. However, we weren't able to meet the ideal range, but that's fine because we have a range where that's like we set up, that's where it's acceptable, so that regardless what the actual outcome is, it's still good, so that we can it's still acceptable. So yeah, so here's a list of some of the accomplishments that we had throughout the 2-semester capstone class. The first one is that we built a board that has a capacity for lip movement tracking. Another one is that we have the speech to lip movement that we can utilize, and another one is voice amplification. And we also successfully tracked the lip movement and display on the screen as well. And lastly, we wrote production level drivers for the flexible screen that we had and the audio. So in terms of drivers for it, the drivers that's available on like internet open source, that for these type of screen, they have the 8-bit drivers. So for this one, we need a 9-bit driver, so that we need to write, it requires 9-bit. The first bit, which is a data like selection thing, so it's not available in the open source, but we need it for our screen instead. So we had to write one on our own rather than just using open source. And here's several lessons that we learned. So one is the complexity of the project. It's the real-time speech to lip sync was really complicated to achieve using based on the hardware limitation we have with the ESP32, and also the libraries that's available for it depends on different language that's available. And also that what main thing we learned is that either we need to verify our footprint or make sure that you make your own so that's correctly, so we don't deal with the issues where something is wrong, but you don't know where it could be wrong. And lastly, it's not written up here, but we also learned that how to work in teams as well, based on each individual strength and weaknesses, and how to assign tasks, different projects, different project tasks to each individual, so that we work in a team as and have good I forgot the word.
Output.
Yeah, right. Yeah, here we have several like phases of this project that should be, currently we have the lip movement that's being used by, we sense through a sensor and then we display on the screen based on the sensor output. But next step, we want to implement the voice amplification to it so that we can hear you loudly if you're further away at distance. So maybe you can't see the screen, but you can still hear us. And then lastly, the third phase, we have the real-time speech to text with lip sync, where that would actually come in play along with the voice amplification, because you want a system where it's detectable by eye, where the delay between the speech and the lip sync, it's not noticeable by naked eye. But you also want a, obviously, where you can hear you further away as well. So that would be our third phase and final phase of this project. So overall, we went through a problem statement where we need to find a solution where to a clear communication while wearing masks indoors. We've gone through our demo of the solution. We've gone through how we came up with the software, how we designed our circuits, and then we've gone through our physical enclosure, our packaging, our housing of the project. And then lastly, we've gone through the different accomplishments, different lessons that were learned, and then the project management part as well. And here's a picture of where we're working in the lab, and that concludes our presentation. Are there any questions?
Thank you. Very good. All right, I'll open the floor.
Oh, I have a ton of questions.
Yeah. Can you run the demo for Dr. Anders? So I can see the demo maybe. Yeah, ask the questions.
You can answer.
And then you can
questions.
answer questions for a minute.
Okay, so I'm coming in very new to the Capstone